Hello everyone and welcome back to this next lecture in the machine simulation series, and this is where we had left off last week, where we had used the block rotor test to compute the remaining parameters of the equivalent circuit. So precisely what we were looking at was to compute all the parameters of this equivalent circuit that represents a single phase induction motor. So in this lecture, what we're going to do, I'm going to correct a mistake that I made last time, and then we're going to print out these values on the screen and figure out and try to interpret these values with respect to any machine and what the significance of these parameters are. So as always, before I start the lecture, a little bit of brief background that if you're interested in these kind of video lectures, but you would like something a little more comprehensive, I do have full-length online courses that you can find on my own website, which is called pythonpowerelectronics.com. And if you go to this website, you'll find these 4 buttons using which you can browse through most of the content of this website, and besides take a few moments to browse through the remaining website. But if you click on this button Learn, it'll take you to the page which has the courses that are currently available. So as of now, I have 5 courses which are available. The very first course is Simulating Power Electronic Circuits Using Python, and in this I talk about the basics of how you can use Python and Python Power Electronics to simulate power electronic circuits. The second course is Basics of Digital Signal Processing for Power Engineers, and in this I talk about how you can use Python and Python packages such as the SciPy package and the signal package within SciPy to analyze and design filters specifically for power engineering applications. The third course I have is called Simulation of Magnetics for Power Electronics Using Python. And in this I talk about how you can use Python and Python Power Electronics to simulate magnetic components like inductors, coupled inductors, and transformers. The fourth course I have is Control Analysis with Python for Grid Connected Converters, and in this I talk about how you can use Python and Python Power Electronics as well as packages like the Python Control package to analyze and design filters or other controllers specifically for power engineering applications, and all the control design is carried out using the case of a single phase converter connected to a single phase grid. And the last course I have is Why Specialize in Power Electronics, and this is a free motivational course targeted mainly towards junior undergraduates or even high school students to tell them about the opportunities and challenges available in power electronics, so that when they do want to make their decision on which they want to specialize in, they could have a better insight into what power electronics offers them. So all these courses are offered on 2 platforms, on Udemy and Decibel Labs, so click on any one of them and choose which you want. So with this, I'll get back to the lecture. So as I said, the first thing I need to do is I need to correct a mistake I made. And the correction of the mistake I made is with respect to the equivalent circuit. So as I said before, in the equivalent circuit, in a block rotor test, we are going to clamp the rotor. So we physically clamp the rotor and prevent it from rotating, due to which the slip is S is 1 because the rotor speed is 0. So under such circumstances, the rotor impedance is negligible and is almost close to a short circuit, which is why the block rotor test for an induction motor is very analogous to the short circuit test for a transformer. Now in a block rotor test, when you do block the rotor, the voltage applied to the stator is very gradually increased until the current flowing through the stator is equal to the rated current. This voltage is going to be negligible, and typically, since the leakage reactance is in the range of around 2 to 3%, that is leakage reactance of the stator, and also the rotor inductance is also in the same range, that is 2 to 3%, this voltage is rarely greater than 5 or 6% of the rated voltage. Right? Applying anything close to the rated voltage to a motor during block rotor test will almost definitely damage the motor. Right? And this is what we had used here as well. We had calculated that we can calculate this series impedance, or rather this impedance of this series path, because in a block rotor test we are assuming this parallel branches to not exist, and therefore this series impedance is equal to the voltage applied divided by the rated current. Now with respect to this, I realized that I made a mistake. For example, if you see, I had coded this as the rated voltage. Again, this is blatantly wrong, because as I said, in the block rotor test, you do not apply any voltage close to the rated voltage, right? Voltage applied to the stator is negligible, right? And the reason is because the block rotor test is very close to a short circuit test in a transformer. So I'm going to comment this out because this is wrong. So what this means is I now have to define, or rather assume, a no load voltage. So for example, if you're performing the block rotor test in a laboratory, you can of course take a voltage, a controlled voltage source, like even a simple variac will do, or you can have a more controllable voltage source, gradually increase the voltage until the rated current is flowing. We measure the current, make sure that it is equal to the rated current, and we measure the voltage across which is being applied. And at the same time, we also measure the power which is being absorbed by this motor, because that power is equal to the ohmic losses of the motor. This is how it is usually done. Now, in the code, I had assumed the power that is power absorbed by the motor during the block rotor test to be 15% of the rated input voltage, rated input power. In a similar manner, I will have to make an assumption here as well. As I said, if you are performing this test, physically performing this test, you do not have to do this. You will be actually measuring this voltage. Here we need to assume. So the assumption we make is that since stator and rotor leakage reactance is around 2 to 3% each, right? The total voltage that needs to be applied will be in the range of around 5 to 6%. Voltage to be applied is around 5 to 6%. And therefore we can say that the block rotor test we can say is around 0.6 into V rated, right? So you cannot apply the rated voltage. We are applying a much smaller voltage, and I am assuming this to be around 6% if we take around 2 to 2.5% leakage reactance for both the stator and the rotor, and we assume a little more in terms of the resistances as well, because there is a rotor resistance and there is a stator resistance. So around 6 to 7%, you can even choose 7%. I would not recommend that you go beyond 8 or 9%, because then you're talking about a fairly lossy motor. So this is usually good enough. Now once we have this, we can then calculate this Z series blocked. I'm just going to compute this, but I'm going to replace this V rated with the V blocked rotor. So this is the new computation of the series impedance with respect to this low voltage that is applied during the block rotor test, right? And with this, the rest of the computations should be the same. So what I'm going to do, since we have already, let's go over to the simulator. We have already added this induction motor model. We have not configured any variables yet. And we can hold off for that because we are still at the stage where we are computing the parameters of the equivalent circuit. So what I would do is I'm going to go and run this simulation just to make sure that there is no syntax error. So let's click on the run button. It says simulation is running, but as I said, always go to the command line and make sure that there is no syntax error. And you can see there is a syntax error. And the syntax error is that I rated is not defined. And quite likely I'm using a different variable as opposed to the variable I had defined first. And that's very likely. Let me go over. First, let me go over and stop the simulation. And let's go over and find out. It is this one, that is R stator is equal to 0.5 rated I stator. And let's look at it. It is I rated, that is I underscore rated. Alright, just a minor error. And these kind of things will always happen, which is why I would always recommend you to run the simulation once so that you at least know you haven't made any silly mistakes such as this. And let's run it again. Again, let's go over, see if there's any other mistake. and now it seems to be running, because this is actually, this is also not running because this is another one. And quite surprisingly, I'm making the same mistake over and over again. Usually the IDE should pick it up. I'm surprised it didn't. And let me just go and give some space here. And let's run it again. Hopefully we have got it right, and yes, we do. You see, there are no errors anymore. So these two silly mistakes were all that was remaining. We are now have at least a working simulation. So now that we've reached this stage, we can start printing it out. So let me go and write print motor parameters, and let's start printing them all out one after the other. So let me leave some space. So print. The first is, let us print the basic manufacturer specifications. So for example, we'll say rated voltage is equal to, and let's use the Python syntax here, rated power is equal to rated frequency is equal to. And of course, when you do this, you must use the format command that comes with Python. So all we have to do is provide the three values. So for example, I can just go and pick out V rated, P out rated, and F rated. That is V rated, P out rated, F rated. So these three are our basic manufacturer specifications. Now that we have this, we can go to the more calculated specifications. So for example, let's go here and find out what all we calculated. We have calculated the input, we have calculated the synchronous speed, and we have calculated I-rated. So let's calculate these. So for example, we'll say synchronous speed is equal to, and we'll say input power, let's call this rated input power, and the last is rated current. And we'll use the format command again. And let me see what these are. Synchronous speed and P in rated and I rated. So these are calculated values. And once we have these calculated values, let's look at now the parameters themselves. So let's look, and we can actually go over and start printing out everything starting from left to right. So first is the stator. So let's print out the stator resistance and the stator leakage reactance or leakage inductance. So we'll say stator resistance is equal to leakage inductance is equal to, and here we can again use the format command, and let's see what these are. These are R stator and this is L stator leakage. And let's keep going. Next in the equivalent circuit are these two, that is a branch, that is a core loss resistance, and the magnetizing inductance. So let's print that out. So core loss resistance is equal to, and magnetizing inductance is equal to, as always, format command, and it needs two variables, which we can go all the way up here, pick out what we need, RC and LM. And let's keep going. The next are these two, that is the rotor inductance and the rotor resistance. So we'll go and we can call this rotor resistance is equal to and leakage, or we can call it inductance also, because and here we will call this R rotor and L rotor leakage, right? So with this we have these parameters. Now remember, it's important to note that this control file will be continuously executed at every simulation instant, right? But we do not want a whole page full of results. So basically, if I run it as it is, this entire page will be full of parameters and I will have to break the simulation. So for that, I'm going to use a little trick. I'm going to just say, give a couple of lines and says put error. The reason is this line is not valid Python syntax. So when it tries to run the simulation, it'll give us everything else until here, and then it'll say invalid syntax. So let's go and run the simulation. And if we go and have a look, we'll see that this is exactly what we get. Unfortunately, it has not showed up, so I will just let it be and just break the simulation. Maybe that's the only simple thing to do. So let me run it. Let's come over here and let's just terminate the simulation. This is something which I usually don't like to do because you're breaking the simulator and you'll have to relaunch it, but not a problem. So these are our motor parameters. So let's have a look. The motor parameters, the first is the rated voltage. As expected, this is already said. We have it from the manufacturer specifications. The synchronous speed, actually this might be a mistake because synchronous speed should not. Yeah, synchronous speed is 3000 RPM, which is correct. So we have a two-pole machine at 50 Hertz. So quite obviously, if you do 2 into F into P divided by 120 or 120 F by P, you will get this value 3000 RPM, right? That is the formula. So for example, if you go over to the code, you will find where I calculate the synchronous speed, it is 120 into frequency divided by the number of poles. This is the speed in revolutions per minute. We have a rated speed of 2800 RPM and we have the synchronous speed which is 3000 RPM, right? So the slip is 3000 minus 2800 divided by 3000 at rated power, right? Now the rated input power is higher than the rated power by this value, that is 2941, and that is, we have assumed it is a 15%, it has 85% efficiency at full load. Again, this value you can change. You can consider a motor which is 80% efficient or even 90% efficient. Going more than that, unless you know for certain that you've done a very special design for the motor and this is a very, very efficient motor, choosing anything beyond 90% is usually not very recommended. Now with all these, you will find that the rated current is around 15.3 amperes, right? And it seems fairly reasonable. If you just divide 250 or even 2500 divided by 240, you will get something in this range, right? So this is something that is fairly reasonable, because remember, we also have to take into account that there is a power factor. Because remember, it is not just simple matter just to divide P in divided by V rated. We also have to take into account this is an AC machine. It draws, besides an active power, also a reactive power component. So therefore, even though you might think that you should get roughly around 10 amperes, It is more than 10 amperes because of the reactive power which is also being drawn. And that reactive power is taken into account using the power factor at rated power, which again is an assumption. Then comes the stator. Now let's look at the stator resistance, which is, you can see, less than even 0.1 ampere, 0.1 ohm. And the leakage inductance is in the range of around 0.006 Henry. That means it is around 0.6 millihenry. The core loss resistance, on the other hand, is around 1000 ohms, because remember, the core loss resistance is in parallel, which means when the rated voltage is applied, this core loss resistance will account for around 1% of no load losses which are being drawn from the motor in order to feed the eddy current losses and the hysteresis losses. The magnetizing inductance now is close to 1 Henry. Look at the difference between the leakage and the magnetizing inductance, right? This is almost close to, one could say, 200 times larger than the leakage inductance, right? I mean, this is 0.1, this is around 0.005. So that is about the calculation which I could compare these with. So the reason is that this magnetizing inductance is responsible for producing the magnetic field in the air gap of the motor. So if you apply a rated voltage to this stator, the current drawn by this branch, which is the magnetizing inductance, is the magnetizing current, and this current is responsible for building the flux in the air gap. So quite obviously it would take a very large inductance to be able to build a significantly strong magnetic field and yet draw a very small current, because remember, this magnetizing current is the inherent cost of a machine, a magnetic machine, but it should not be large. If it is prohibitively large, then you will have a lossy machine, because this current drawn will produce ohmic losses as well. So therefore, the reason, and that explains why you have such a large magnetizing inductance, right? Because remember, by basic definition, flux linkages is equal to current multiplied by inductance. So therefore, the larger is your inductance, the stronger the flux you can produce with a smaller current. And then finally we come to the rotor. The rotor resistance, on the other hand, you can see is much larger than the stator resistance, and this is by design. So if you come over here, you see we did not choose the rotor stator resistance to be equal to the rotor resistance. The reason, the stator resistance is the resistance of the windings, which is much lower. On the other hand, the rotor resistance is the resistance of the rotor bars, which are short circuited. These are very, very different entities. Therefore, these two are quite different. The rotor resistance is much larger than the stator resistance, right? And the inductance of the rotor has been assumed to be equal to the leakage inductance of the stator, and therefore we have the same value. So this is a quick recap of what we did in terms of computing the parameters of this motor, right? Again, I would strongly suggest that go ahead, play around with these values, right? Most importantly, play around with all these values and also some of these assumptions. So for example, assume a different value of efficiency at rated power. Assume a different power factor rated power. So instead of using 0.8 power factor, choose 0.75, 0.86 or 0.88, whatever you want, right? So these are things that I would always suggest that go ahead and try them out. And later we can even look at number of poles being greater than 2. So we have multiple poles in the machine. So with this, I'm going to end this lecture, because now we have a motor, we have calculated the parameters of the equivalent circuit, and we can now use these parameters in our model. So with this, in the next lecture, we will gradually start, and I'll just remove all these because this is just for the purpose of describing the physical significance of these values. But in the next lecture, I'll get rid of all this, and we will start with the actual machine modeling. That is, building the magnetic model of this induction motor. So if you have any doubts, feel free to either message me on social media or send me an email, whichever is your preference, or I will see you next week, where we will begin using these parameters to start simulating the induction motor. Thank you so much for watching and see you soon. Goodbye for now.